Okay. So we're talking about limits and infinity, right? Section 2.4. Limits and infinity. Right. So before this time, before this section, we're talking about something like this: x approaches c, and the limit is L, right? And both C and L are some finite values, right? So C is some actual number, right? And L is also some actual number, right? But last time we started talking about something like this: as x approaches C, f of x tends towards infinity, right? Tends towards infinity, and we don't think of infinity as a number that you heads towards. It's not like there's some number up there called infinity that's higher than all numbers, and you're heading towards infinity. But rather, this is just a way of saying that the value increaes without bound, right? So we have this definition, right, that Does anyone want to try to state how we describe going to infinity? The phenomenon of a function heading off towards infinity. What did that mean? Okay, can anyone describe it? Emily, go ahead.
Just the y value as you're just asking what a function looks like if the limit is infinity?
Yeah, well, I mean, you can give it to me roughly. You can give it to me, like the definition. The definition would be, so there's sort of a couple ways you can think about an idea. One is just like roughly, right? That, for example, here, as your inputs get closer to C, your outputs get closer to L, right? So that's sort of like the layman's description of limit, right? And then we have the sort of the professional description of limit, which is, for every epsilon greater than 0, there's this delta, so that if you have this thing around here, then blah blah blah, right? And then you can have also sort of like an intuitive feeling for that professional description, for that actual mathematical description, right? Which is you have your intuition, right? Given any distance around here, we can find a place where that tolerance is satisfied, right? Which is something quite different from the initial description that we gave, right? So, yeah, Rachel.
There's a vertical asymptote at x equals c.
Okay, so there's a vertical asymptote there. Right. So at x equals c, there's this vertical asymptote. Right. Maybe you're going like this or this. I guess if we're talking about just plain old infinity, we go like this. Can anyone give me a sense of the actual definition? Yeah, Ellie.
Is it for any line m on the y-axis? Yeah. Then the limit's going to be greater than that?
Yeah. So almost. Yeah. Very good. Given any line or given any height, say m. Given any height m, so let's change the picture. Change this thing. So, given any height m, there is a place in which there's an interval around C, right? There is a interval around C, centered around C, interval centered on C, in which all f of x exceed m, right? All except maybe at C itself, right? We don't say anything about what happens at C itself. Okay. So given any height, there's an interval around here where you exceed that height, right? So for example, if I were looking at, suppose I'm looking at 1 over the absolute value of x. Okay, 1 over the absolute value of x, and I'm looking at the limit of that as x goes to 0. Right? That's going to be infinite. Right? What's the picture look like? What is the picture of 1 over the absolute? What's the picture of 1 over x? Somebody just gesture. Right. 1 over x, you know, looks like this. Right. 1 over the absolute value of x, of course, everything's going to be up. Right? Everything's going to be positive. Like this. Okay. And suppose I say, it looks like it's going off to infinity, and if I ask you then, give me an interval in which your function exceeds 10. Give me an interval around 0 in which your function exceeds 10. Right? So I put a bar here, right, at height 10. And I say, can you give me an interval in which your function exceeds that value? Right? Well, write it down. Take 10 seconds and write it down. Okay. What's the interval? Who would like to tell me what the interval is? Or do you want to talk to somebody? Talk to somebody next to you for another 10 seconds, and then I'll ask you. Okay, so who would like to say it? Who would like to tell me? Helen.
Well, we were sort of thinking, we know that x can't be 0, so we were thinking like 0 to infinity, but not including 0.
So we want an interval where all the values are above 10, right? We want an interval in which all the values are above 10. So if I choose, for example, like 100th, if I choose like 100 over here, right? Well, then my value is going to be 1 over 100, so it's too low, right? I don't want to use the whole space here. I want an interval around 0 where all the values are higher than 10, right? So Ruchika.
Just a question. If the graph is 1 over the absolute value of x, as x gets bigger, won't you get smaller numbers? And basically if you have like 1 over, oh, I see, that's why 0 has to.
So
Like, well, then what would the interval be? You can't be like x is x like less than 1 and greater than 0? Is that what the interval?
Well, let's see, right? We want an interval. Remember, we want an interval centered on 0. So it'd be like negative something, comma something, right? Negative 1/10 and 1/10, yeah, right? So negative 1/10, right? Negative 1/10 to 1/10, right? Because as long as you're, right? As long as the absolute value, what you're saying is that the absolute value has to be smaller than a 10th, right? Because if the absolute value is smaller than a 10th, then certainly 1 over the absolute value is greater than 10. Right? Is greater than 1 over 1/10, right? So whenever this is smaller than that, then 1 over x is going to be greater than 10, right? Or another way to see it is that you say, well, look, I know this function is increasing as you head towards 0, And I know that at 1/10, I get the value 10. And at negative 1/10, I get the value 10. So anywhere between there, I'm going to be higher than 10. Right? Okay. So however you want to think about it, right? Okay. So now suppose the value is 100. Right? So I make another bar. I say, can you find me a plate? Can you find me an inch bar around here where you exceed 100? Well, what is it? Negative 1/100th, comma 100th, right? And if I say 1 billion, I'm sorry, if I say I'd like to exceed a billion, well, you'd say negative a billionth, comma 1 billionth, right? And so you see that no matter what bar is set, there's an interval around 0 where you exceed that bar, where all values are higher than that bar. Okay? And this is what it means to head towards infinity. This is what it means to have a limit of infinity. Okay. So just to this is what we said last time, but just to re-emphasize it. Okay. So right. So we talked about this, and we talked about vertical asymptotes. Let me write up the sort of more. So given any m, there exists a delta, so that if x minus c is less than delta and greater than 0, then f of x is greater than m. So this is the more notation-heavy way of writing the same thing here. Okay, and if you can see that these two are the same thing, you're in a good position. Okay, so let me translate. Right? Given any m, there exists a delta, right? So this delta there exists a distance to 0, right? There exists a distance to c, so that if your distance to c is smaller than that and not equal to 0, then your values all exceed the bar. Okay, so you see that it's saying exactly the same thing, right? Given any height, there's some distance. Given any height, there's some distance. Here it is. There's some distance to c, so that if the distance of your point to c is less than delta, but greater than 0, so you avoid c itself, then the height of your output is higher than m. So it's exactly the same thing. Okay. Does everyone see that it's exactly the same thing? Ask this part. If you don't see that, then please ask. Joe, you have a question. Okay. So now let's go to the second half of 2.4. Second definition of 2.4 is this one. So just change this. X goes to infinity, and the limit is out. So infinity is now what x is heading towards, right? And you have a finite limit now. The limit isn't infinite, but rather the inputs are heading towards infinity. Okay. So take 1 minute and see if you can write down what you think this ought to be. What should this be in see if you can have an idea of what this ought to mean. Just like for the first one, we had there are these bars that you exceed, blah blah blah. There's given any bar, there's a place where you exceed that bar. What should this mean? What should this mean? I'll be impressed if you can do it. I don't expect you to do it. If you can't do it, that's perfectly normal. But see if you can do it. Okay, would anyone like to venture a guess or make a try at it? Tete, go ahead. Yeah.
Could it be something like a horizontal asymptote?
It will be, yeah. So horizontal asymptote is good, right? This basically, if this happens, this is the same thing as there's a horizontal asymptote. Yeah. Okay. Now, so you have some picture at least now in your head, right? There's some line, right? And your function is getting closer and closer and closer and closer to that line. Your function gets arbitrarily close to that line. So how do we describe that using, does anyone have a guess on how to describe that using the notions that we've, basically like taking apart the notions we've had before and putting them back together in the right way to describe this sort of phenomenon? Edie, go ahead.
I like this picture up here.
Okay.
So you say choose any point C, any point that you want, and there's an interval around it, C plus delta.
Wait. This is not the same thing. This is the picture. This is the picture.
I like to. You can go to infinity on the x-axis.
Oh, okay. You want to. Okay, so.
So forget the y-axis.
Okay, so here we go. You like this picture better?
Yeah.
Okay.
So you can choose any point C in the interval delta C plus delta C minus delta, such that f of x. Choose any point m, such that the absolute value of f of x minus m is less than any epsilon that you choose. You can get smaller and smaller. So you'll find a point C such that this interval, any x's in this interval, will cause f of x to be less than that.
Okay, great. Okay, so what you're saying is this. You're saying, given any epsilon, right, there's a place, right, there's a C and a delta, right? And a delta, right?
Yeah.
There's given any epsilon here, a plus delta, a minus delta, there's a C and a delta, so that in C minus delta, C plus delta, the following is satisfied. Right, that's what you're saying.
What is that last word?
The tolerance is satisfied.
Satisfied.
It's no better.
Yeah.
Okay. What do you think about that? Does that seem like it captures the notion of infinity, like heading off towards infinity? Does anyone have another way of would anyone like to modify this a little bit so that it is more in line with what they think goes in with infinity? Okay, Edie, it's a good guess. Let me show you something that will satisfy your definition, but won't satisfy what we think. So you could have a function that goes like this. Saying, okay, well, here's my function. My function is going to go up, it's going to drop down, and it's going to equal your function. Equal L for some time. And then it's going to run away. Okay. And I'd say, oh, look, this satisfies your definition. Because, look, no matter what epsilon you give me, I can find a place where the tolerance is satisfied. Here it is. Here's it is. Right? The tolerance is satisfied in this interval. Okay. Right? In fact, every tolerance is satisfied in this interval because my function actually equals L there. Right? So for any epsilon you give me, I'm just going to choose this. This will be the place where it happens. Okay. So not quite, but it's a good try. It's a good try. Would anyone like to? Yeah, Emily.
Well, I was thinking about how oscillating things may still approach, like asymptotic infinities. Yeah, exactly. They can still approach the same value.
Yeah.
So I guess past some certain point C, the absolute value to that whatever is.
Very good. Very good. Very good. Very good. You get 2 points or 3 points. I'm going to give you 3 points on the next exam. That was very good. Excellent. Okay. So yeah. So past. Given any tolerance, there's some point past which that tolerance is satisfied. Past which that tolerance is satisfied. Okay. So given any epsilon, there exists some point, and usually we use the letter n. There exists some point n past which f of x minus L is smaller than epsilon. Okay, so by past which means that is, i.e., for if x is bigger than n, then f of x minus L is less than epsilon. Okay, and that's the definition of heading off towards infinity. I'm sorry, of the limit being L as x goes to infinity. Okay, so yeah, and so like we just said, let's see. Yeah, so for example, right, again we could look at, say, f of x is 1 over the absolute value of x, right? F of x is 1 over the absolute value of x, and as x goes to infinity, this thing goes to 0, right? And you see that, right, it's going to look like this. And if somebody wants you, so we're saying that the limit is 0. If somebody wants you to stay within epsilon and minus epsilon, right? Somebody says, oh, if the limit is 0, you should be able to stay this close to 0. Well, how far along do I have to be? What is my n? What's my n? The function is 1 over x. What do I take as my n? What n is such that past that n, all my values are between negative epsilon and positive epsilon? You're thrown off by the epsilon. 1. 0.1. Yeah, 1. What if I need to stay between -1 and 1, Alfred?
Well, I was going to say 1 over epsilon.
1 over epsilon, yeah, thank you. 1 over epsilon will do. Right, so as long as I am right at 1 over epsilon, right, I'm going to hit that value, and then I'm going to get closer to 0. Past that point, I'm always closer than that to 0. Right. Right. So, so actually, my 1 epsilon is here. Right, because that's where I hit that value. And then past that point, I see that for all x bigger than 1 over epsilon, 1 over the absolute value of x is smaller than epsilon. Right? Just like before. Okay. So here's, this is the idea. And like we said before, this is right, if the limit is L as x goes to infinity, we say y equals L is a horizontal asymptote. Horizontal asymptote. Okay, so when this happens, we say the thing has a full horizontal asymptote. I should say that sometimes people say, "Oh, you're not allowed to touch the asymptote, right? This is not an asymptote because your function is not allowed to touch it. It's okay. The function can touch it." I'm not sure why people say this. All we mean is it just has to be that the limit is that value, that the function becomes arbitrarily close to that line as you go towards infinity. That is, you can make the function as close to the line as you desire. Okay. Any questions? Emily?
If you're oscillating like above and below your limit,
Yeah.
can you get like, so usually you get like really small and really close, can you get significant and then still?
So that would fail then, right? I mean, if it, unless, right, so if you have some guy that becomes very close and then it leaves it, right, and it doesn't become arbitrarily close again, then that's no good, right?
Is that's still, it's still true because the limit is approaching L?
No, still the limit's not approaching L anymore, because I could say, I'd like you to stay this close.
Mm-hmm.
And you'd say, there's no point past which I always stay that close.
So this is like the hard definition.
Yeah. So this is, you have to be that given any tolerance, there's a time past which given any tolerance, there's a corresponding time past which that tolerance is satisfied.
So what was that, sine x over x? Does that not have a limit?
So if you look at sine x, for example, sine x
Right,
is point sine x itself, right? As x goes to, well, that's going to be like this, right? No limit.
Mm-hmm.
No limit.
Okay.
Yeah. Right. Like what? There's no value. What value would be the limit?
Well, 0, because it's like the limit. But yeah.
Yeah. But if I do something like this, say, then your function would look like this. Like that, right? And then that would have a limit. That guy would have a limit. Really, by the this would have a limit by the analogous squeeze theorem, right? By something along the lines of the squeeze theorem. So for just maybe we'll say it. I was going to say it in a couple of minutes, but right now, limits at infinity. Also have their own squeeze theorem. Right? If you have three functions, one big, one middle, one in the middle, and one below, and the upper guy and the lower guy both tend to a limit as you go off to infinity, then the one in the middle will also. Right? So here in this picture, we have this guy and this guy, right? And they're both going to go to 0. So the guy in the middle, no matter how crazy, is going to go to 0 also. Okay. Just a reminder about horizontal asymptotes and how one calculates them. Right. So here's the sort of the standard trick of calculating horizontal asymptotes. So somebody says, let's look at x squared plus x plus 1 over 3x squared plus 2 as x goes to, say, positive infinity. It could be negative infinity. Doesn't matter. Okay, as x heads off towards positive infinity, the game that one usually does, the trick that one usually does is the following. You multiply the top and bottom by 1 over the height. You multiply by a cleverly chosen 1. Okay, 1 over x squared or 1 over x squared, that's 1 actually. Multiplying by 1 is okay. So you multiply by a cleverly chosen 1. You say, okay, well, this is the same thing as the limit as x goes to infinity of this thing over x squared, it's 1, plus x over x squared, plus 1 over x squared. And on the bottom, I get 3 plus 2 over x squared. Right? And then, right, what happens as x goes to infinity? Well, the top is going to head to what? Not 0. 1. Right? The 1 stays still. 1 over x goes to 0. 1 over x squared goes to 0. Right? So we end up with, 1 on the top, and we end up with 3 on the bottom. So it becomes. So you know that your function has a horizontal asymptote of y equals 1/3. Eliza, you have a question?
Oh, no. Sorry, I just middle scene, but I got it.
Okay, sorry.
It's all right.
Okay. I think probably you've all seen this sort of trick before. Okay. Now, if we have something like this, sine of 2x over, say, say 1 plus, no, let's just say x squared. Okay. I guess I've already told you what's going to happen. What's going to be the limit as x goes to infinity? Don't blurt it out, but what will be the limit? Don't blurt it. But yeah, it will be 0. And why? Why? You can't play the same game that we did here. So secretly over here, what we're using is that the limit, if the top limit and the bottom limit exist, then the limit of the quotient is going to be the quotient of the limits. Right? We have this theorem for finite limits about this sort of thing. Right? The limit as x approaches c, the quotient is going to be the limit of this guy over the limit of this guy, as long as they both exist and the bottom guy doesn't go to 0. Okay. Right, so secretly that's what we're doing here. But here you can't do that, right? The bottom goes to infinity, the top oscillates. Yeah?
Squeeze theorem? The squeeze theorem?
So we use the squeeze theorem, right? So you say, well, okay, we don't know what this thing is, it oscillates too much, right? But we're going to trap it. We're going to trap it between, say, negative 1 over x squared and positive 1 over x squared. Eating, yeah.
And you can do that because the sine of 2x has boundaries. On
That's
top and
right.
bottom,
That's
so
right.
you can put it in between that.
That's right. Sine 2x goes between negative 1 and positive 1. Right? So at the lowest, this is going to be at negative 1 over x squared. At the highest, this is going to be at positive 1 over x squared. Okay? And then you'd use the corresponding squeeze theorem, and you say, well, I know that this thing goes to 0, and this thing goes to 0. So by the squeeze theorem, the limit of the middle guy exists and equals that shared limit. Rachel?
Can you kind of do it more intuitively and just look at, like I looked at and I was like, okay, well the values of sine of something as the something gets bigger and bigger, are gonna change like normal sign, and then the bottom is gonna be infinity is gonna be big, so it's gonna be 0 because the bottom's.
Yeah, I mean that's the intuition. That's basically what's happening. To justify it, one uses the squeeze theorem. To justify that intuition, one uses the squeeze theorem. But yeah, if you didn't know anything, if you didn't have the squeeze theorem, you just think, well, I'm pretty sure that's what's going to happen. So yes, Alfred.
So does this limit actually touch 0? Because technically sine, didn't sine cross over 0?
Yes, but it's okay.
Oh,
Yeah. So it's perfectly fine for a function to touch the line that is its horizontal asymptote. I don't know why. I don't know why people come in with this maybe, yeah. But I think that they're actually told this, that no, you can't. You're not allowed to touch the horizontal asymptote, right? How many of you were told this? You can't touch the horizontal asymptote. Yeah, it's strange. I don't know why that. It's okay. It's okay. How about dividing by an irrational number? Sometimes students come in saying, you cannot divide you cannot divide by an irrational number, right? Like you cannot divide by the square root of 2. Say, it's wrong to divide by the square root of 2. We say no. It has to be 2 over the square root of 2. No, you have to be the square root of 2 over the square root of 2 over 2. You have to rationalize the denominator, because otherwise something will happen. But these are the same number, right? These are the same numbers. So I'm not sure why one is forbidden and the other is not forbidden. Yes, Edie.
Do you have regular office hours this afternoon?
Yes. Are you gonna tell me why?
I'm working through some of the odd number problems and I don't know the answers, and so I just need some more.
Oh, sure.
review.
Sure. Okay. Yes. Okay. Okay, so there's one last thing in 2.4. I was actually planning to go through 2.5 today, but let's not. There's only 10 minutes left. We'll do 2.4, and then I'll hand back a tremendous pile of stuff, including the last exam, the first exam. Okay, take it easy. Take it easy, right? So right, in any case, I think the first exam is worth half of all subsequent exams, right? So remember that even if you do poorly on this exam, the next 2 exams are worth double it, right? And then the final is worth maybe triple it. Okay, so does it make you feel better or worse? I'm not sure. In any case, don't worry too much at this point. You can worry later. Okay, so here's the last notion in the chapter. The limit as x goes to infinity is infinity. So who would like to think of how we should describe that? Rachel.
I just would propose a function that would work that would y equals x work.
Sure. So if you have f of x equals x, that's going to be something that we think of as tending towards infinity as the inputs head off. So, right, that's a function that you think of as heading off towards infinity as the inputs head to infinity.
So would it be something with a slight asymptote with that?
For this function, yes, but you need not have a line that you approach. Right? You could have something that just keeps on rising, say. Right? Does anyone want to? Maybe I'll just say it unless somebody wants to try. Okay, so I'll tell you. So it's this. Given it's just a combination of the two other definitions. Given any bar, Who wants to complete the sentence? Given any height, there exists a there's some point n, very good, past which, right, f of x exceeds the bar. I should give you Leon, a point for that. Okay. Right. Given any, all right. Yes. Okay. So given any bar, there's a time so that if x is past that, so that past that time, all your values exceed n. Right? So given any height, there's a time past which you are higher than all values are higher than that. Okay, and that's as you see that makes